Welcome to the fourth laboratory session. So today we are going to see how to determine the thermal conductivity of a bad conductor using least disk method. So let us see what is thermal conductivity first. So thermal conductivity, or I can say if the amount of heat that is flowing through a conductor will be proportional to its area, time through which the heat flows, and the existence of temperature gradient. So amount of heat flowing through a material will be directly proportional to its area, the time of heat flow, as well as to the temperature gradient. If I put a proportionality constant, then Q is equal to K into A into T into dt by dx, where this K you call it as coefficient of thermal conductivity or simply thermal conductivity. Now, if you want to find what is the value for this thermal conductivity, then rearranging this equation a little, we have K is equal to Q divided by A into T into dt by dx, right? So if A is taken as 1 meter square, that is area of cross section of the material is 1 meter square, and if the heat flow is assumed to be for 1 second in a conductor, and if the temperature gradient is maintained to be 1 Kelvin per meter, then we can say K is equal to Q. Or in other words, thermal conductivity can be defined as amount of heat flowing through a material of unit area of cross section for 1 second when it is maintained at a unit temperature gradient. Right? So that is what the definition for thermal conductivity is. So thermal conductivity can be defined as the amount of heat flowing per unit area of the material per unit time when it is maintained at a unit temperature gradient. Now, what is the unit for this coefficient of thermal conductivity or thermal conductivity? Let us go on to the equation. This equation, the unit for Q, that is amount of heat energy, that will be expressed in joules. Area, the unit is meter square, and for time it is second, and for dt by dx, this represents change in temperature and this represents change in distance. So we have Kelvin per meter. So this meter get cancels with this meter square, and this joule per second can be written as watt, right? So watt, which is the unit of power, that is joule per second, can be written as watt. So this joule per second is written as watt divided by, you have a meter here and a Kelvin here. So watt divided by meter into Kelvin, or simply we can write it as watt meter inverse Kelvin inverse, which is the unit for thermal conductivity of a material. Now let us see what are the apparatus that is required to do this experiment. You want to have a least disk apparatus, a disk for which you need to find the thermal conductivity, and it should be a bad conductor, and you do need to have 2 thermometers, a stop clock, a screw gauge, and a vernier caliper, right? Let us see the experimental setup. So this is a vessel where it is filled with water. So when you switch on this induction, the water in the vessel will start to boil. When it reaches 100 degrees Celsius, the water will get vaporized, and the vapor will pass through this rubber tube, and the other end of the rubber tube is connected to the steam chamber. This is the least disk apparatus. It has a steam chamber and a least disk, right? This is what you call it as a steam chamber, and this you call it as a least disk. This is the least disk, which is a simple metallic disk, a thin metallic disk, and you have a steam chamber above which I have kept the bad conductor whose thermal conductivity has to be found, and above the bad conductor I have kept the least disk. Now what happens? In the steam chamber, you have 2 openings. That is, here is the inlet, that is for a passage of steam into the steam chamber, and here there is an outlet which is used for taking out the water that is condensed in the steam chamber, right? So to collect the water, we are having a pan here. So when the steam chamber, and another, there is a hole over here for the steam chamber which is used to keep a thermometer. A thermometer can be used to measure the temperature of the steam chamber. So we can keep a thermometer inside this steam chamber. So if you check the temperature of the thermometer in the steam chamber, it will be at room temperature. When steam starts to fill the steam chamber, the temperature of the steam chamber rises and it will reach a maximum of 100 degrees Celsius, which is the temperature of steam. So when the temperature reaches 100 degrees Celsius, it will remain constant, right? It is the maximum temperature that can be attained in the steam chamber, and it will remain constant at 100 degrees Celsius. Now in the first part of the experiment, we need to find out the steady state temperature of this steam chamber as well as least disk, right? So this steady state temperature of the steam chamber will be equal to 100, right? So we can take the steady state temperature of the steam chamber as 100 degrees Celsius, or sometimes you will be getting only 97 degrees Celsius, right? Due to the surrounding temperature, heat might be lost and it might attain a maximum of only 97 degrees Celsius, and converting it to Kelvin will be having 370 Kelvin. What is this? This is the steady state temperature of the steam chamber. What is steady state temperature? It is the maximum temperature that is attained by the steam chamber. It is constant with respect to time. So at whatever time you check the temperature, it will remain constant at 97 degrees Celsius. So that represents the steady state temperature of the steam chamber, which is taken as θ1. Now we had kept the bad conductor whose thermal conductivity has to be found above the steam chamber, and above the bad conductor you are keeping the least disk, right? So bad conductor, it will not allow heat to pass through as quickly as a good conductor. It is, as the name itself says, it is a bad conductor, right? It will not conduct heat very fastly. So it will conduct only a little amount of heat, right? It is not an insulator. It is also not a good conductor. So let us put a thermometer into this least disk also to measure its steady state value. So least disk also has a hole as a provision to insert the thermometer. Now what happens is the steady state temperature of the steam chamber is noted down as 97 degrees Celsius, and since there is a bad conductor in between the steam chamber and the least disk, not all the heat will be conducted from the steam chamber to the least disk. So initially, if you check the temperature of the thermometer that is inserted into the least disk, the temperature will rise a little and it will not reach 97 degrees Celsius, which is the steady state value of the steam chamber, but it will reach a maximum of around 80 degrees Celsius, right? Maximum, for say for example, it might reach around 80 degrees Celsius, right? So why it happens? Because there is a bad conductor in between the steam chamber and the least disk. Depending upon the thermal conductivity of this bad conductor as well as its thickness, the steady state temperature of the least disk will stay around some 80 degrees Celsius, right? So after a steady state is reached by the least disk, note down the temperature in the thermometer on the least disk as steady state value, right? So initially the temperature on the thermometer which is inserted into the least disk will rise. It will never reach 97 degrees Celsius or 100 degrees Celsius, but it will reach, depending upon the thermal conductivity of the bad conductor as well as its thickness, it will reach a steady state value that is much less than 97 degrees Celsius. Say for example, let us take it is equal to 72 degrees Celsius in our case, right? So let us take the value as steady state temperature of least disk, that is θ2, as 72 degrees Celsius. If you convert it to Kelvin, it will become 345 Kelvin. Right? So this is the first part of the experiment where you are going to find the steady state value of steam chamber, the steady state temperature of least disk, θ1 and θ2. Now what you are doing is, please remove the thermometers on the least disk as well as on the steam chamber. Remove the bad conductor which is in between the steam chamber and the least disk. You just remove the bad conductor and keep the least disk in direct contact with the steam chamber. What happens now? Steam chamber is at 97 degrees Celsius, least disk is at 72 degrees Celsius. They were in direct contact with each other without bad conductor in between. Now if you put a thermometer into the least disk, you can observe the rise in temperature in the least disk. Why the temperature rises in the least disk? Because now the least disk is in direct contact with the steam chamber. Now if you check your thermometer, the thermometer shows an increase in temperature, and again the thermometer will go to a maximum of 97 degrees Celsius, which is the temperature, steady state temperature of the steam chamber, right? So after the thermometer shows a temperature which is almost some 10 degrees greater than the steady state temperature of the least disk. Say for example, if the least disk is steady state temperature of least disk is 72 degrees Celsius, you allow your least disk to be in direct contact with the steam chamber until your least disk reaches 82 degrees Celsius. That is theta 2 plus 10 degrees Celsius. Right? So after this least disk reaches 82 degrees Celsius, you remove the thermometer, you switch off the induction stove and try to hang this least disk in air. Now the least disk is hanged in air. It is not in contact with the steam chamber. It is hanged in air. Now switch off your induction stove and keep the thermometer back into the least disk. Right? Now what happens to the temperature of the least disk? The temperature of the least disk will start to fall. Why it is falling? Because the least disk is now hanged in air. We are not supplying any heat energy to the least disk. So the surrounding temperature is almost 32 degrees Celsius. Least disk is at a higher temperature, that is at 82 degrees Celsius. So it will start transferring heat from itself to the surroundings, and hence the temperature of the least disk will start to fall. Once the temperature starts to fall, you keep a stop clock ready, and once the temperature comes to theta 2 plus 5 degrees Celsius, that is, we have heated this least disk up to 82 degrees Celsius, which is 10 degrees greater than the steady state temperature of the least disk, that is 72 degrees Celsius. Now allow the least disk to cool to 77 degrees Celsius, right? Allow the least disk to cool to 77 degrees Celsius from 82 degrees Celsius. Now, when the temperature on the least disk is 77 degrees Celsius, you switch on the stop clock. Make sure the reading is reset and you switch on the stop clock. Right? At 77 degrees Celsius, you are switching on the stop clock. So, for 77 degrees Celsius, the reading should be taken as 0 minutes. Right? And for each degree fall of temperature in the least disk, you need to observe what is the reading on your stop clock. Say for example, when the temperature falls to 76 degrees Celsius, here the observed reading is equal to 0.26. Why you are putting it as 0.26? 0 represents minutes and 26 represents seconds. Right? So now the time is equal to 0.34 seconds. Right? When this pointer rotates one complete rotation, then it will become 1 minute, right? 60 seconds will become 1 minute, and try to observe what is the reading on the stop clock when the temperature falls by each degree Celsius. Say for example, if your steady state is 72 degrees Celsius, steady state temperature of the least disk is 72 degrees Celsius, you keep the least disk in direct contact with the steam chamber until the temperature goes to 82 degrees Celsius. After it reaches 82 degrees Celsius, you switch off the induction stove and hang your least disk in air. Now the temperature of the least disk will start to fall. When it falls to theta 2 plus 5 degrees Celsius, that is 72 plus 5, that is 77 degrees Celsius. When the temperature of the least disk falls from 82 degrees Celsius to 77 degrees Celsius, you try to switch on the stop clock and take the reading for stop clock reading for 77 degrees Celsius as 0. Right? Now observe the reading for each degree fall of temperature in the least disk. You should not switch off the stop clock until you completely took all the readings. Right? You have to start your reading from 77 degrees Celsius, that is theta 2 plus 5 degrees Celsius, up to theta 2 minus 5 degrees Celsius, that is up to 67 degrees Celsius. Right? So you need to observe what is the time in the stop clock from 77 degrees Celsius to 67 degrees Celsius for each degree fall of temperature. You can write it in minutes. When once the pointer crosses one complete rotation, you can write it as 1 point. If it completes 2 rotation, you can write it as 2 point and check what is the reading on the stop clock, on the pointer. Right? If it completes 2 rotation, then you have to write it as 2.26. 2.27, that's it, right? So that is how you need to take readings in the stop clock. So once when you switch on the stop clock at theta 2 plus 5 degrees Celsius, you need to switch it off only at theta 2 minus 5 degrees Celsius. That is, if the steady state temperature of the least disk is 72 degrees Celsius, keep it in direct contact with the steam chamber and raise its temperature to 82 degrees Celsius, that is theta 2 plus 10 degrees Celsius, and make your least disk to hang in air so that its temperature starts falling from 82 degrees Celsius to 77 degrees Celsius, that is theta 2 plus 5 degrees Celsius. When it comes to theta 2 plus 5 degrees Celsius, you switch on the stop clock and take the reading as 0. You monitor the thermometer which is kept on the least disk. When the temperature reaches 76 degrees Celsius, you check what is the reading on your stop clock and note it down in the appropriate place in the table. And when it falls to 75 degrees Celsius, note what is the reading in the stop clock. You need to repeat the procedure. You need to note down the reading on your stop clock for each degree fall of temperature in the least disk until the temperature of the least disk goes to theta 2 minus 5. In our case, theta 2 is equal to 72, so 72 minus 5 is 67. You need to observe the stop clock reading from theta 2 plus 5, that is 77 degrees Celsius, to theta 2 minus 5, that is 67 degrees Celsius. So this is what the observation is. And after you observe for theta 2 plus 5, you can switch off your stop clock and you can reset it. And now you need to do a graph. So the graph is to be drawn between time on x-axis and temperature in y-axis. And remember, we have taken temperature in degrees Celsius. So put another column to convert it to Kelvin. That is, if you add 273 with the 77, you will be getting 350 Kelvin. This is temperature in degrees Celsius. Here it gives temperature in Kelvin. And stop clock reading is in minutes. You just convert it to seconds, right? 0.26 will give you 26 seconds. 1.05 will give you 1 minute 05 seconds, right? 1 minute is equal to 60 seconds. So 60 plus 5, 65 seconds. Similarly, you can convert all the readings in minutes to seconds. You have to draw a graph by taking this temperature in Kelvin along y-axis and stop clock reading in seconds along x-axis. This is the model graph. Time is taken along x-axis, temperature is taken along y-axis. You will be getting a curve like this, right? At steady state temperature, you can draw a line representing the steady state temperature. Let me show you the sample graph here. So here is the sample graph. As you can see, time is taken along x-axis in seconds and temperature is taken along y-axis in Kelvin. Please remember, it is in Kelvin and this is in seconds. Now you will be getting a downward trend like this. You just draw a line corresponding to 345 degrees Celsius, which is the steady state temperature in this case. So you draw a line to that point which corresponds to the steady state temperature. You need to observe the slope. You need to calculate the slope in between the points that just lies above the steady state point and below the steady state point, right? So this is the point that corresponds to the steady state temperature. You just draw a line from the steady state temperature along y-axis. Then you consider a point just above this point and just below this point. Now you need to calculate the slope between these 2 points. This will give you d theta. Now the temperature is represented in theta. So this represents d theta and this represents dt. So you can calculate what is the value for d theta by dt, right? So you can write scale for the graph. In x-axis, 1 centimeter is equal to, see here, it is now taken as 25 seconds. See here, 0, 25, 50, 75. So each of this centimeter represents 25 seconds. So in x-axis, 1 centimeter is equal to 25 seconds. And along y-axis, see here, this is 343, 344, 345. So each centimeter represents 1 Kelvin, right? So in y-axis, 1 centimeter is equal to 1 Kelvin. Now you need to find what is the value of d theta by dt, right? This will give you the value of d theta and this will give you the value of dt, right? Say for example, if 345 Kelvin is the steady state temperature, your taking slope for 346 and 344, that is 152 and 239 seconds, right? So dt will be equal to 239 minus 152 and d theta will be 346 minus 344. That will give you the value of d theta by dt. You can calculate d theta by dt. It will be in Kelvin per second. This is the value of d theta by dt at steady state, right? Around steady state. So d theta by dt is equal to some value. You can take 4 digits after the decimal point, Kelvin per second. Because x-axis is in second and y-axis is in Kelvin, so d theta by dt will take the unit of Kelvin per second. Right? Now let us check the formula to calculate the thermal conductivity. Now K is equal to ms into d theta by dt around theta 2h plus r into d divided by 2 pi r square into h plus r into theta 1 minus theta 2. This m represents, see here, m represents mass of the least disk, which you can get it from the manual. S represents specific heat of the material of the least disk, that is in joule per kilogram per Kelvin. You know, specific heat capacity is nothing but it is the amount of heat required to raise the temperature of 1 kilogram of substance by 1 Kelvin. That is also a constant. You can get it from the manual. And d theta by dt you are getting from the graph, that is the slope of the curve in the graph around theta 2. And here the sketch represents the thickness of this least disk, right? The thickness of the least disk can be found using a vernier caliper. You can use a vernier caliper to measure the thickness, right? You can measure the thickness of this least disk using a vernier caliper and you can take it as sketch. Let me show the table also. So this represents the thickness of least disk H by vernier calipers. So value of main scale reading, vernier scale coincidence, these two you can observe by keeping the vernier caliper at 3 different places on the disc. Calculate what is the observed reading, calculate what is correct reading, take mean, that will give you the value of H in 10 power minus 2 meter. And the next variable you need to have is this R. R represents radius of the least disk. How will you find radius of this least disk? You can make use of a thread to measure the circumference of this least disk, right? You make a thread and you keep a thread around the circumference of this least disk and try to find what is the value for circumference, right? Circumference of least disk is given by 2 pi r, right? 2 pi r is equal to, you find what is the value of 2 pi r, circumference of the least disk, by using a thread and making it and measure it using a meter scale. You will be finding what is the value of 2 pi r. From this you can calculate what is the radius of the least disk, which is nothing but that value you are finding divided by 2 into 3.14. That will give you circumference of the least disk. Let me show you that also. So see here, 2 pi r is equal to, the circumference of the least disk came as 34.5 centimeters. So 34.5 into 10 power minus 2 meter divided by 2 into 3.14. That will give you radius of the least disk. And the third variable you need to use here is the thickness of the cardboard, which is given by this D. Right? This D represents thickness of this bad conductor, which you can measure using a screw gauge. You can use the screw gauge to find the thickness of this bad conductor. And again you have to find the thickness by keeping the screw gauge at 3 different places. You need to observe what is the value of pitch scale reading, what is the value of head scale coincidence. You need to calculate observed reading as well as correct reading after finding 0 error and a 0 correction, which is written over here. And you can find the mean value, that will give you small d, which represents the thickness of the bad conductor. Now you can substitute all the values. You can see here the observed readings are written here. Mass of the disk is written as 950 into 10 power minus 3 kilogram. Specific heat of the material is 380 joule per kilogram per Kelvin. That is for the least disk. And this is the calculated value of d theta by dt from the graph we had plotted between time and temperature. And this represents radius of the least disk, which was calculated by measuring the circumference. D represents thickness of the bad conductor, which was measured using screw gauge. And H represents thickness of the least disk, which is measured using a vernier caliper. Now we have noted down already the value for steady state temperature of the steam chamber as well as least disk as 370 Kelvin and 345 Kelvin. See here we have written the value of steady state temperature of steam chamber as well as least disk as 370 and 345. So these are the observed values. Now if you substitute all these values in the formula, you will be getting what is the value for coefficient of thermal conductivity or simply thermal conductivity, whose unit is watt meter inverse Kelvin inverse. I hope you understood how to determine the thermal conductivity of a bad conductor using least disk apparatus. Thank you.